visualize what we've now got by bringing up a motion view. And we've got a hell of a lot of channels, as we can see. What we want to do is to delay these channels according to which point they were taken from. Now, there are at the moment 6 attributes connected to each point, 3 rotation attributes and 3 position attributes. So we can use a delay job to achieve what we want. Well, let's see whether that works. At the moment I'm delaying everything by the same amount, but we can see what's happening here. The delay, which is here at frame 50, everything before frame 50 is 0. And that's not going to be what we want, because that's going to mean that at frame, let's just make sure we can see our house. It's going to mean that if we bring in our animation back from CHOPS, the house is going to start in position and then going to fly away and then fly back again. So it's a real problem that the delay introduces this area which is 0 here. It would be better if we could get the position to stay and rotation to stay as it was during the delay period. Well, fortunately there is another job which can do that for us, and it's called the shift job. And the shift job just moves everything slightly to the right, and we can use the scroll offset, and as you can see with the shift job, the value stays at its initial value during the delay period. So I need to enter an expression here to ensure that each point has a different shift. So let me use floor $C over 6. Now $C is the channel number, and we know we've got 6 channels in each point, so $C over 6 gives us a unique number for each point. And the floor function makes sure that we get an integer. So this gives us something to create our delay with. Let's say we're going to create a 0.1 second delay. The other thing I'm going to do is use a random function again based on $C over 6 to add a little bit of extra delay. And let's stick a null on the end of this, and I'm going to call this CHOPS out. So to see the effect of our CHOPS network, we're going to have to bring those attributes back into our SOPs network, and we do that using a channel SOP, and the CHOP that we're going to bring it from is CHOPS out, and I'm going to include our rotations as well, and this should allow us to visualize what's happening. And of course it has to be animated. So we're getting our planks flying in one after another. So far, so good. So the next thing I would like to do is to introduce a little bit more animation into or rather a little bit more variation in the animation in our scene. And I'm going to do that in the CHOPS network by adding a stretch chop. And what a stretch chop does is lengthen, stretch an animation curve by a certain amount, and I'm going to do that by adding a random offset to the length, or rather a random scaling factor to the length of each curve. And that introduces yet more subtle variation into the movement of our planks. That takes us through the things that we have to do in CHOPS. The next step is to bring the rotation animation back onto our planks. Let's do that by going inside our house network and setting up a number of variables here which we're going to use in copy stamping. And I'm going to call them Rx, and the value of that is $R1. And if you remember, we set up our attribute $R, which contains the rotation information, and it will have three variables, R1, R2 and R3, associated with its three components, and they'll have different values for each point. So what we're doing here is setting up a variable Rx, which is different for each point based on $R1. Similarly, set up Ry and Rz. And now we need to introduce a transform SOP in order to take advantage of those attributes. And the way we do that is to use the stamp function inside the transform. And stamp takes as its first argument the node, which you're using to copy stamp. In this case, it's our copy node. Then it takes the name of the variable that you're copy stamping with, and then it takes a default value, which I will give as 0. Then I'm going to copy that, let's enlarge this, and paste that expression into the other values, except of course I need to change this to Ry and this to Rz. And what we should find is that as our planks fly in, they rotate. But there's a problem. As we can see, they're rotating in the wrong direction around the x-axis, I think. So let me try making this rotation negative and try again. And now we can see that they are all flying in correctly.